Hey guys, so far we've been looking at protocols that are not very common. These protocols, the routing protocols and things like that, are not very common and not exactly common knowledge. Now we're going to look at some common protocols. These are protocols that you would see every day in a corporate environment. These are protocols that you should know a lot about. The other ones, maybe not so much. You probably won't ever use those except maybe setting up a large enterprise network. But for what you're going to be learning most, what you're going to be doing most, these protocols that we're going to look at now are going to be a lot more useful. So let's go ahead and look at the desktop. Okay, common protocols, module 6, section 4. There are 3 common types of protocols: management, communication, and security. Those 3 sets of rules are going to be present in every corporate network that you can think of. Go ahead and do the participation activities. NMB and SMB are very common. NMP, and SMB. Server message block protocol is a client-server communication protocol used to share files, printers, serial ports. Basically, it can carry anything. It can carry transaction protocols for interprocessing and implementing in Microsoft Windows. SMB is something that you need to be familiar with because it can also be taken advantage of. Network management protocols, that is a suite of protocols. That's multiple protocols for defining the processes, procedures, and policies to manage a network. If you're a network administrator, NMP will be very important to you. Monitors the network 24/7 in real time and provides network statistics to the administrator. The statistics provide information on use and routing, and also things like unexpected events and downtime, or some when components, routers, or whatever go down. 2 common network protocols are ICMP, which is the protocol that ping uses. So if you ping another computer, you're using the ICMP protocol. And Simple Network Protocol, SNMP. Information, an NMP protocol provides status of a host, if it's up or down, how the route is to it, if it's got a lot of bandwidth problems, if it has bottlenecks or whatever. Host availability, is it actively available on the network? Network latency, if you're familiar with lag, if you've ever played a game and you've been killed because of lag, that is a product of network latency. Packet loss, when you ping, do you get 3 received and 1 lost, or 2 received and 2 lost, or is everything showing up like it's supposed to? And then finally, network errors. If there are multiple IP addresses that are duplicates on the network, if there are any kind of network error that you can think of, NMP will make reports on that. Okay, once again, participation activities are important. ICMP, and that's the protocol that we use to ping things with. It's a protocol used by network devices to communicate problems with data transmissions. It's a network layer 3, just like IP. And since ICMP is a network layer protocol, it has no port numbers. You don't have to worry about TCP or UDP. Anything operating below level 4, which is where TCP and UDP live, they're not going to use port numbers. You can't ping a port specific, or you can ping a port specifically, but you're not just using pure ICMP. It's a component of the TCP/IP stack. It accompanies IP to provide the process for sending control and error messages. It relays messages as datagrams containing IP header and then ICMP data. Its function is to report any IP operation errors. And common messages are time to live, TTL. Basically, that sets the lifespan of a datagram. Destination unreachable. This is where ping occurs. So if you can't reach the destination that you're trying to ping, you'll get a destination unreachable message because the IP packet's destination host or network or whatever is not reachable. Parameter problems. When a device finds a problem that's not covered in any other ICMP message, it will send back a kind of generic error message and then packet too big. This used to be a real problem. Once upon a time, when you could control how big the ping packets were that you sent, you could send a malformed packet in a ping across the network and you could take a whole network down. Nowadays, routers are programmed to respond to this and to deal with it, and they will filter out those malformed packets. But once upon a time, packet too big was a real problem, because that was one way of hackers attacking a network, is to send a ping, but with the packets being too large. And so the network would try to react to it and it would die. So participation activities, make sure you're getting these done. SNMP, Simple Network Management Protocol. It's a network protocol for monitoring and managing network devices on an IP network. Basically, if you've got switches or routers or things like that, you want to control them over the network, you can do that with SNMP. It uses ports 161 and 162, and those are TCP ports. So that tells you that it operates above layer 3, and in fact, it operates in layer 7. It's an application layer. A managed device, like a switch or network element, is a network node that implements SNMP and allows access to the network node's information. For example, a managed device can be any type. It can be a switch, a router, cable, modem, anything that is smart, anything that you can manage remotely through an interface on another computer. So SNMP Manager is a system that monitors and controls that particular device's activities. An agent is the software that runs on a network element and collects and maintains information. So SNMP Manager may request information from a network element or set configuration parameters. You can control and configure smart switches over the network without having to go to the switch and plug in a serial port. An SMP agent listens and executes the commands sent by an SMP manager, and a trap is an alert message sent from SNMP to a manager to notify the manager of an event at the network device. Managed information base is an ASCII text file that describes the elements as a list of data objects. Once again, participation activities, and then ARP. Address Resolution Protocol, ARP tables. This is how switches keep up with what's on their ports. It's a network protocol for mapping dynamic IP addresses to physical MAC addresses. So we're familiar with the MAC address. That's the address that's burnt into a piece of hardware, like a network card or a switch. And an ARP table, or Address Resolution Protocol table, it acts like a DNS database for a switch rather than a router. So a router uses DNS to map URL addresses to IP addresses. If you go to Microsoft.com through a router, the router doesn't understand Microsoft.com, but it does understand the IP address. And so the DNS server will send back to the router and say, oh, you're trying to get to Microsoft.com, you want to go to 196.154.25, whatever. An ARP table does the same thing with a switch. A switch may have 8 or 16 or 24, however many ports, and it needs to know what IP address is attached to each one of those ports. So when you plug a network cable in, the switch queries that, whatever's on the other end of that network cable, and gets the MAC address, and it puts it in an ARP table, so that when the switch gets information, and it gets data packets that it needs to send, it knows where to send those, so it doesn't just flood the network. It doesn't just flood every port. Otherwise, you'd never get anything sent, because the switch would constantly be sending every time it got a packet, it would send copies of that packet to every single port, and your network would be flooded. So basically, there'd be a bottleneck at every switch. But because the ARP table is there, the switch can say, okay, I need to send this to port 14 or port 15, whichever port the thing is plugged into that you're trying to reach, and all those other network ports on the switch don't get flooded with that information. That is essentially what an ARP table does. The protocol that's used to do that is the Address Resolution Protocol. So it maps IP addresses on a network to the physical MAC addresses. ARP works between the data link and the network layer protocol. So it's down low level between 2 and 3. It does not use a specific TCP port because it's too far down the OSI model. It functions with IPv4 addresses. ARP functionality in IPv6 is replaced by NDP, or Network Discovery Protocols. Hackers can try to exploit ARP. Dynamic ARP inspection, for example, is used to detect and reject invalid or malicious ARP packets. An application like HTTP Hypertext Transfer Protocol sends requests to an IP address. As the information moves down the OSI model, a MAC address is needed for delivery to a destination device. So layer 2 provides the MAC address for the destination, and ARP table is what the switch uses to look up the MAC address corresponding to that IP address. If the IP address is not in the ARP table, then the source device broadcasts an ARP request. Everything on the network has to send back its MAC address. The ARP request is a broadcast message asking which device has the requested IP, and that requested IP device sends back a unicast with its MAC address. And then the switch says, oh, okay, so this packet belongs to you here, and it sends it. Another participation activity, and that should take care of section 4. So guys, if you have any questions, contact me through the Canvas inbox or let me know during class, and I'll do my best to answer these questions.